everyone, welcome to week 3. In today's lecture you'll need to print off homework number 4. That's 8 pages, the 8 pages, 52 questions. We'll be working today up through the dark line. I think it's on page 6. You'll need the solutions formulas Word document that you can find right underneath homework 4 on Joule in week 3. You'll need your calculator, your periodic table, and your pink sheet. These two things are mostly just for reference. Okay. So today we're going to learn all about mixtures. There are 2 different classes of mixtures. There are heterogeneous mixtures, and there are homogeneous mixtures. The heterogeneous mixtures you are all already familiar with in your medical practice. All suspensions are heterogeneous mixtures. So all of the antibiotics that come in the bottled formula, or some of the antibiotics that have the base that the pharmacists have to make up in the lab in the hospital, those are all suspensions. Anything that you have to shake, or anything that has little particles that settle to the bottom, those are called suspensions, and they are heterogeneous solutions. Heterogeneous means that things in your solution, SOLN is how I'm going to abbreviate the word solution for the rest of today. Okay, so heterogeneous solutions mean that things in the solution are not evenly spread out. Anything that has something that's settling to the bottom, like orange juice, when you have the pulpy kind of orange juice where all the little flakes of the oranges settle down to the bottom and you have to shake it before you pour a glass, that's a suspension. Those antibiotics, like I told you about, those are suspensions. Kids Motrin, that's a suspension. A lot of things in cooking are suspensions. If you make most kinds of dressing, because they include the oil part and the vinegar part, those things separate. So when you shake them, you're trying to disperse those flakes or particles or whatever. You're trying to disperse it more evenly by shaking it. If you think about pouring a glass of orange juice, if you didn't shake it before you poured it, all those little pulpy flakes would be left on the bottom, and then when your juice got done, there'd be a whole mess of the pulp. But if you shake it, it's a little bit more evenly distributed, so when you pour it, you can actually pour those little flakes of pulpiness. That's a suspension. The other type of heterogeneous mixture that I want to call to your attention is something called a colloid. Colloids are also suspensions because they're not evenly distributed, but colloids are special because they're particles in the solution reflect light. Snow is a classic example of a colloid. You all know from your years of driving experience that when you're in that really hypnotizing, blinding snow, you don't ever turn your brights on. The reason is because snow is a colloid, and every single one of the snowflakes is going to reflect light from your head beams, or from your headlights. It's going to reflect that light back at you. If you turn your brights on, there's even a higher concentration of light particles that are going to be bounced off of the snow particles, and it's just going to bounce right back at you. So you're going to see when you turn your high beams on an even brighter column of white snow. That's very hazardous, and that's why we don't drive with our high beams on in that snow. Fog is the same thing. Let's write some examples here for you. Fog snow, antibiotics, OJ. Fog is the same way. So if you turn your high beams on in a foggy environment, all of the light is going to be reflected back at you off of the little particles in the fog. The fog is really just water vapor that is visible, and so you have all that light coming back at you, and that's hazardous. So the difference between colloids and suspensions, in colloids you have particles that reflect light back at you. There's a fancy chemistry name for that, but I won't tell you about it. Okay, there are 3 specific types of homogeneous mixtures. Another word for homogeneous mixture is solution. When we use the term solution in chemistry, we mean something that's a homogeneous mixture. Well, what does homogeneous mean? Homogeneous is something where things are spread out evenly, and that means perfectly evenly. So that if you were to take any sample from anywhere in your solution, it would be exactly the same as every other infinite number of samples. Okay, so one of the specific types of homogeneous solutions is a gas plus gas mixture. So a lot of times we just think of solutions as something that you pour, liquidy. But anything that is uniquely and evenly spread out in a container is called a solution. So gases are infinitely mixable. So that means that because their molecules are traveling so far apart and they move so fast, that gases, when you put 2 of them in a container, they're going to be evenly distributed, forming a solution. The most common example of a gas plus gas solution is air, the air that you're breathing. The air that we're breathing is not just oxygen. It's a mix of a whole bunch of different gases. There's a lot of oxygen, that's the most prevalent gas, but there's a little bit of nitrogen gas, a little bit of hydrogen gas, a little bit of carbon dioxide, that's what we're exhaling. All of those gases are part of what make up our atmosphere, and they're all evenly distributed throughout our personal spaces. So therefore, air, the air that you breathe, is a gas plus gas solution. Another kind of solution is a solid plus solid solution. Okay, the best example for you of a solid plus solid solution is a topical ointment or cream, whichever one you want to think about. So sometimes you're required a doctor is required to give out a prescription for some sort of topical treatment. And sometimes the pharmacist needs to make that up in the lab. It's called compounding. And so what he or she has to do is take a certain portion of, let's say, hydrocortisone cream, for example, and some other base, maybe the base cream would be like an aloe type base. And they have to mix those 2 things so that they are spread out evenly, so that the hydrocortisone medicine is spread out evenly in the base cream. They don't want to just prescribe the pure hydrocortisone because that is too high of it's too concentrated, it's too high of a dosage. And so they basically dilute it with that base substance. Once the pharmacist is done compounding, the resulting ointment or cream is a homogeneous mixture. Therefore, topical ointments are solid-solid solutions. Another example of a solid-solid solution would be gold jewelry. So if you have some gold jewelry that's 14 karat or 10 karat or 18 karat gold, that number of carat is what percentage of pure gold your piece of jewelry is. The higher the carat, the higher the percentage of gold in the compound. For example, 24 karat gold is 100% gold element. There are no fillers or anything, and it's very, very soft. It flakes off. And if you're familiar with the Goldschlager liqueur, there are actually those are real pieces of real gold flecks on the bottom of your Goldschlager bottle. That is 23 karat gold, and anything that's higher than 23 karat gold is actually edible. It's one of the rare metals that a person can consume and not suffer from heavy metal poisoning. So anything less than 24 karat has to be combined with some other metal to form the solution. White gold is a combination of gold and silver. Rose gold, which has become pretty popular lately, is a mixture of gold and copper. That's what gives it the kind of pinkish color. And if you're familiar with Black Hills gold, you know that there sometimes is rose gold and then there's that green gold. The green is from aluminum. So aluminum is mixed with the gold to form a homogeneous solution, and that's how you get your jewelry. Well, those things are interesting and fun things to talk about, but the thing that we are going to spend all of the rest of our time on are the aqueous solutions. And an aqueous solution is where something is dissolved in water. I hope you all can see that. Okay. So whenever you have something dissolved in water, you're going to see that AQ symbol. And we talked about this last week in reference to things that were soluble in water and things that were insoluble. Anything that's soluble gets the AQ designation, meaning that it is in watery solution. Okay. What is a solution? A solution is made up of two parts. You have a solute plus a solvent. And when you add them together, you get what's called a solution. Okay, now, these are chemistry words, and I'm going to transfer them into English for you. A solute, in English, that word means a thing which is dissolved. So, you put a little of your table salt into some water for boiling, for maybe making some noodles or something, and all of the salt disappears. What happens to it? Well, it's not magic. What happens is that the salt dissolves into the water. So when a solute dissolves, the solute disappears because it becomes one with the water. So that's sort of what we mean when we say the word dissolved. Solvent also has an English translation. Solvent is a thing that dissolves other things. It is the dissolver. want you right now to write on your paper really, really big H2O and circle it, and let's put some happy stars here around here. The reason is because water is known as the universal solvent. It is able to dissolve more things than any other dissolver. And water, because it is the universal solvent, can never, ever be a solute. Water can never be a solute. Water can never be a solute. I said it 3 times because it bears that much emphasis. Even if you have a solution that is 99 parts salt and 1 part water, the solvent is still the water. Water can never be a solute. Okay, now, for the rest of our time, we're going to be talking about how to actually calculate different concentrations for solutions. There are 5 different concentrations that we'll be talking about, and there's a specific methodology for solving each one of these problems. We'll do several examples for each type so you can feel comfortable about them before starting the homework on your own. However, this is the methodology that you'll follow for every kind of problem. We're first going to write a table of knowns and unknowns. I'll take you through this step. This is the second most important part of the problem. And yes, you must write it for all of the problems in order to get full credit. Then you must write down your formula. This is where you'll go back to the formula sheet that you printed out. And then step 3. Step 3 is going to be the hardest, but the most important part. You're going to want to solve your formula for the unknown value. This means that you're going to have to do a little algebra. If you're rusty on your algebra, please call me and I can talk you through how to do it. The 4th step is to do some what we call plug and chug. And that just means put the numbers in for their variables, hit the buttons on your calculator, and write down the right answer. Step 4 is the least important part of the process, even though that's where you're getting the answer. It's all in the setup. So if you ask me a question like, Michelle, I don't get how to set it up, well, then you don't get the whole problem. You don't get the whole concept. You need to be more specific about that so I can know how to help you. And when you're finished with your plug and chug step, you need to make sure you're using correct sig figs and units. On your learning check for this lecture, I put a lot of trick answers that have wrong significant figures. So make sure that you're careful when you're doing that learning check that you've got right sig figs and units, because I was really tricky about it. Okay, so let's talk about the first type of solution, and then we'll get through how to use all those 4 steps. The first type of solution that I want to talk about today is what's called the weight per volume percent. So we're going to say it like this. So these little letters in English mean weight per volume percent. That's really obnoxious. Weight per volume percent. Okay, so a couple of things then we need to WT stands for weight. V stands for volume, and the percent sign is percent. Okay, so what does this mean? Well, the way you're going to calculate weight per volume percent, look at your formula sheet. You'll see that it says there weight of your solute, and that should be always in grams, divided by the volume of your solution. And that should always be in milliliters. Now, for every problem that has a concentration where you have a percent, you're going to multiply by 100 in order to get the percent. Let's just give a little tutorial on how to use percents and numbers real quick. Okay, so after you do a division problem, let's say that my score on a test is an 82 divided by 100. The number you get for that when you're actually doing the real math is 0.82. Now, that doesn't mean that I have 0.82%. That's not what that number means. If I want to actually calculate what the percent is, I have to multiply by 100, therefore giving me 82%. So that's how you go from a number to a percent. Let's talk about going from a percent to a number. Let's say that I am going to Kohl's and I got my 30% off coupon in the mail. And let's say that I wanted to buy my husband a tie, and the tie was $10. Okay, to calculate how much savings I'm going to get, I don't multiply 30 times 10, because if I did that, if I took 30 times 10, that would give me 300. That's not what that means. That obviously makes no sense. If I'm going to try to buy a $10 tie and I have a 30% off coupon, I'm not going to save 300 bucks. So how do we use the number then? Well, we have to take this 30% out of the percent and use it as its real number. So when you're going from percent to the real number, you're going to do this. Take your 30% and divide that by 100. That turns a percent into a number that you can use. So 30 divided by 100 is 0.3. So that means that I can take that 0.3 times the 10, and I know that I'll save 3 bucks on that $10 tie. So with my 30% off coupon, it'll only cost me 7 bucks. Okay, so that's how we're using percents. So when we calculate the weight per volume percent, in order to get that number into percent, we have to multiply by the 100. Okay, let's just do a little algebra review here. I know I told you that you should call me if you're having problems, but I think it would be best if I just showed you how to do it right away. Okay, so basically algebra means I just wrote Allegra. Oh, brother. Algebra means that you're going to solve an equation for one variable. And the way we use algebra to solve equations is by undoing what our equation tells us to do. Okay, so you're always going to be what's called undoing the operation in the existing formula. So if I have A times B equals X, and I always want to solve for X, I'm going to make sure that my equation, in my equation, I always have X by itself. Okay, well in this case, X is by itself. So here we have a formula that's solved for X. And when you're solving for your one variable, that means that you're going to get that value, that variable, by itself. Okay, so we said that this equation is solved for X because the X is by itself alone on one side of the equal sign. Okay, well, what if I have something like this? A times X divided by B equals C. This is a tricky one. We need to get X by itself. So in order to do that, we're going to have to get rid of A and B. Now, I'm going to take you through this one step at a time. If you're okay on algebra, you can skip ahead. But I would suggest that most of you watch this to make sure you're doing okay. Okay, firstly, I'm going to get rid of this A. In my base formula, I'm multiplying A times X. In algebra, we're going to be undoing whatever our formula is telling us to do. So instead of multiplying by A, I have to divide by A. Now, the cardinal rule of algebra is that whatever you undo on one side, you have to also do that to the other side of your equation. So I'm going to divide both sides by A. That is going to cancel out those two A's. And that means that I'm left with, on the left side, X divided by B equals C divided by A. Okay, that wasn't so bad. But now I still need to get rid of this B because X is still not by itself. So here we're going to have to multiply or divide by B. Well, you have to undo what you're doing in your formula. Here we're dividing X by B. The opposite of divide is multiply. So I'm going to time both sides by B. That is going to give me, I apologize if this is not linear, X is equal to C times B divided by A. Here we have X by itself on the left side of the equation. This is where I prefer to put the X. So in this case, if it makes more sense for you that X is on the left, you can just flip this reaction around. This equation, I should say. X equals A times B. X equals A times B is the same as A times B equals X. That is how you solve for X. That is how you use algebra. Okay, I'll be walking you through the algebra for all of the example problems that I'll be doing tonight. So hopefully by the time we're done with tonight's lecture, you'll get a hang of this.